Okay, question 4M8 from Statistical Rethinking, second edition. Before you run the code, of course, make sure that you have installed and loaded the Rethinking package in R. So question 4M8 asks us to modify a model that is presented in the chapter. It's the last model presented in the chapter. It's the Splines model. So if you don't know what splines are, you should really read the chapter, but hopefully you can kind of glean enough of it here. So the data that we'll be working with is a data set called cherry blossoms, and that's in the Rethinking package, and we are just looking at cases for which this particular variable called DOY are available. So just rows where this value is included. So let's look at our data set here. So we're just looking at D2. And so you'll notice it's a long data set. There's these ellipses here, so it goes on a very long time. And each row is a particular year, and the year is recorded here. And then DOY represents, this is the thing that we're modeling, this is the day of the year at which the first blooming of the cherry blossoms is recorded. Okay, so 92 days into the year, 812 cherry blossoms were blooming. Okay, yeah, and these variables here we're not going to use. Okay, so there's 827 years that we have data for. So let's get going here. So first we need to build our splines. And to do that, we need to define some things here, and then you'll see how these come into play in the next block of code. So to build our splines, we need to bring in the package called splines, and then we use this command from splines called BS, which I believe must stand for basis splines, and then we're going to put that into an object that we're calling B. Okay. So this is going to define x values, and then it's going to give us y values. So we say what years or what rows in the data do we want to index on. And then this is going to spit out the y values, and you'll see what this looks like in a second. But so first we need to define knots, okay? And a knot is basically an anchoring point somewhere along the x-axis that our curves are going to bend around, okay? And so we've passed it an object that we already created called knot list, okay? And then there is degree, which we have defined as knot degree. 3 is typical for this. So what's going to happen is our splines, we're gonna draw lines between each of the knots, each of these anchors. And if we have a degree 1, then these lines are just completely straight, and when we hit a knot, we take a sharp curve in the direction of the next line, and so on and so forth. But by making it degree 3, we're creating cubic polynomials, which are very smooth. So we would want smooth curves rather than very harsh, sharp curves. So I've ran this, but let's take a look at B here. So B gives us this great big matrix, okay, of 827 rows, which is the number of rows we had in the data set, and then it has 17 columns. Each column is representing an individual spline, an individual curve over the 827 years of data that we have available. Okay, so this matrix, it's not really easy to make much sense of, so let's look at a graphical output. Okay, so here is all of our different splines. Okay, and along the x-axis we have year, so this is all of the rows of our data, and then each column in our object B is represented by one of these curves. Okay, so if we look at the first curve, the first spline here. So we have a value of 1, okay? And so you see we have a value of 1. And then as we go down in years, or go down, which means across in years, the values of that spline go down and down and down. And so that is what's being represented with this curve here. And if we go to the second spline, we start at 0 and go up for a while, right? And that's exactly what we have here. And it will eventually decrease, although we're just showing 6 rows here, so we don't get to it falling back down. And the same goes for every one of these curves here. Okay. Oh, something I should mention. Why are there 17? So we defined 15 knots, but why are there 17 splines? It's because we need to also account for the very beginning and end of the data. So additional splines are tacked on. Okay. So now what we want to do is we want to figure out, so we need to modify each of these curves and squish them down or inflate them or whatever the case is so that it begins to resemble our data or to fit our data. And the way that we're going to do that is each one of these splines we're going to multiply by a weighting parameter, and we need to estimate that weighting parameter. So in other words, this curve is going to have its own weight, this curve is going to have its own weight, this curve is going to have its own weight, and so on, and it's going to stretch or shrink some of these accordingly in order to fit the data. Okay, so we need to estimate those weighting parameters, and that's what this model here is doing. So let's just quickly walk through the model. So D is the thing that we're modeling, and that is just doi. We've redefined doi or day of year as D here. Okay, and it's modeled as a normal distribution with a mean mu and standard deviation sigma. And mu, here's our linear model with A, the intercept, and then B, which again is this thing that we've created defining all of our splines, multiplied by W. And W is the parameter, is the weight that we are trying to estimate to figure out how to change these different splines to fit the data. Okay, so this model will estimate W, or W for each spline. Okay, so I've already ran that. And when we look at it, you'll notice that there is, it estimates parameters for each of the weights as well as alpha and sigma. Okay. But that doesn't really tell us anything. So we need to visualize this. So we're going to extract samples from the posterior distribution that we just created and plot them. So this is just this, where each one of these curves has now been multiplied by the estimated weight value. Okay, so every curve here is accounted for, and it's been squished or expanded according to the weighting parameter that has been estimated. Okay. But again, what we want is really just one curve that is trying to show us the trend for D for the variable DOY. And the way that we're going to do that is at each x value, we want to kind of take the average of all vertically intersecting lines here. So this point right here should be kind of the average of here and here. And so this is the code to do that, and I won't talk too much about it because we've already discussed the link function and the HDPI and so on and so forth. But the bluish dots, these are the actual data points, and then the gray curve here is a what does it use here? I think a 97% credibility interval around a line that could be there that would just kind of be right in the middle of all of this, that represents the trend in DOY. Okay, so that's what was in the chapter, and now we are meant to modify the model in a couple of ways. And the first way that we are supposed to do it is to increase the number of knots. And so I'm going from 15 to 30 knots. You can try different numbers of knots here. And just to see what happens to the posterior distribution. And so I'm going to run this, and I apologize because it takes a second or so to run. But notice that all I've done is increase the number of knots. Okay? And we can see that I've increased the number of knots down here, right? So this is our unweighted basis splines, right? And so you see how condensed that is compared to when we started, right? So there's more curves in there. And then these are the weighted curves. So we ran the model, And now we've estimated weights for each of those curves, and now I've taken the average at each x value, and I get this. Okay, so how does this look in comparison to the previous output? And you'll notice that it's a little bit wigglier, okay? And this should make sense why this is wigglier. Well, there's more splines, and so there's more places for this curve to kind of bend around, okay? Now, the next thing that we're supposed to do is to increase the prior distribution on the weighting value. So in other words, when this next model goes through to estimate the W values, the weight values, its prior distribution, rather than being 10, which it was above, is now 100, which means it can explore more areas. It's going to entertain more values as being potential values for these W values. So what do you think then is going to happen to this plot? Okay, so let's run that, and while it's running, think about how the resulting plot might look if we can entertain more weighting values. Okay, so here it is right here, and to my eye, and what should be the case, is that we have become wigglier still. Okay, and why is that? Well, the reason is because we have removed or decreased the constraints placed on these values of W. So each one of these curves here it can assume different values, or can be estimated as different values because of our prior. And so as we remove these constraints, either by increasing the size of the prior distributions or increasing the number of splines, we get wigglier. And what that wiggliness is suggesting is that this model more precisely fits the data. Just a glimpse ahead, that may not be a good thing. So the reason is because, so it's called overfitting, and the book will discuss this more in later chapters, but just a look ahead. This data represented by these blue dots is partially signal, right, that is somehow carried in the year, but some of it's just noise, randomness. A warm front moves through for a couple of days that has no significance to a larger trend, and those random or unimportant or those noisy attributes of the data are more likely to be picked up as we decrease the constraints on the model. And so there's going to be a balance between wanting flexibility in our model and wanting to constrain it to whatever assumptions we're making. But that'll be discussed later. Finally, I think I'm going to make another spline model dealing with circadian rhythms, and specifically with sleep. So when I finish that, I will put a link in the description. Okay, thanks.